This slide presents a proposed pre-versus pulse generator for 3D NAND. For the slide number 1 and 2 already presented in another presentation for the pre-versus pulse circuit theory, and please review that first. And in that previous presentation, I stressed on the impact of the RC, the time constant variation, on the effectiveness of pre-versus pulse design. This table shows the quantitative the properties. In the middle shows the no RC variation case, and plus 20% and minus 20% variation in RC time constant. When you apply the step pulse to word line, the delay time should be varied by the same amount of RC time constant. In this example, when this delay time is used as the unit of 1, then the delay time increases or decreases by 20% when the RC time constant varies by the plus minus 20%. On the other hand, when you apply the P pulse to word line, even though you get the RC time reduction for all the cases, however, the effectiveness degraded when the RC time constant varied. In this example, you can get 70% word line delay time reduction in case of 0 RC time constant variation, whereas your word line, when your word line RC time constant varied plus minus 20%, the word line delay time reduction is estimated by minus 30% or minus 20% for each case. This indicates that the circuit designer must solve the large influence of process variation on the delay time. How can you minimize that effect? In the previous or the prior art, they use the calibration before use. On the left, this is a case for the column driver for flat panel display, which has also a large array. Therefore, column line has significantly large R and C plastic elements. So at the beginning, right after the flat panel display turns on, the user cannot use at that moment. You have to wait for a certain time to execute calibration. So they apply the column line with various heights of p-bars and then measure the delay time, actual delay time, to identify an optimum pulse shape. Once you identify the optimum pulse, then that parameter is set for the following use. So this can be done every time when your display turned on. So there is an overhead in time. On the right hand side, so this is for the wide-range driver for 3D NAND. They place dummy blocks next to array and to measure the resistance value of that dummy block during the probe test. So every single die is measured for wide-line resistance value. They should have the table between the resistance value versus optimum pre-resistance pulse. Then, based on the measured resistance value, you should know the optimum pre-resistance pulse, and that the optimum parameters are programmed into every single die. And in this method, they need additional cost for die size and also the test cost. So if you want to reduce the cost, you would need to have p-pulse generator, which doesn't require calibration. This graph was also presented in the previous presentation, but I'll review this again. This is a graph, the delay time versus RC product error, meaning zero error indicates a target RC value case, and the designers must consider the plus minus 20% variation across the die, or across wafers, or across the rods. When your p-pulse width is fixed at the value, when the RC value is just a target value, then if your wide line RC varied by some amount, the improvement in the delay time could reduce like this. So the target or theoretical line, when the optimum pulse is always available, we should get the 70% improvement regardless of RC product variation. So this is a goal for proposed circuit. How you can do that? Let's look at the borderline voltage at any position x and any time t after pre-emphasis pulse. This is an approximated equation. When you apply the p-pulse of an optimum value given by this equation. Let's input this value to t, and also let's input L to x. So what do you want to do is we want to find the voltage at the furthest node at t equal t opt. That value is expressed by this equation, and you see no RC time constant here. So you know the alpha, parameter alpha, of course, that parameter is designed by you, and you know the target voltage E, of course, and therefore prior to applying the p-pulse to borderline, you know this voltage called Vref. So what you should do is doing the following three things. Monitor farthest voltage node, detect when that voltage reaches Vref. At the moment, you should change input voltage from alpha E to E. When you do these, you actually do T opt applied to the borderline. So let's think about like this. All the equations is scaled by RC time constant in t time. So suppose when your borderline RC time constant increases by a factor of 2, then this curve should have the twice as large as the delay time as the normalized case. So all the behavior is scaled by RC time constant in horizontal axis, but there is no change in the vertical axis. Therefore, you just need to monitor and detect the farthest voltage, whether the farthest voltage reach the left. This is a circuit system to do those three things. Detector places at the furthest node of borderline, and monitor the farthest voltage and compare to the left. The voltage generator should generate a VLEF, alpha E, and E. When the detector output DET is flipped from 0 to 1, the controller changes the value for V in from alpha E to E. This is a simulation result. These dots show a simulated result. All of them are on the line of theoretical minimum line. Therefore, regardless of RC variation, you can get 70% reduction in water delay time. These two waveforms show the farthest and 1/3 of word line in case of plus 20% and minus 20% variations. As you see, the voltage approaching to the target voltage at farthest node and 1/3 symmetrically. To validate this theory, we fabricated a circuit like this. The VLEF is input from external. You can vary the VLEF. VLEF error indicates the error from this theoretical VLEF. The y-axis shows the normalized delay time. If you look at this minimum point, that occurs at 0 error, meaning if you set VLEF expressed by this equation, then you get the minimum delay times, regardless of alpha. This measured data also show the effect of VLEF errors or input offset of detector circuit on the delay time. We also measured the delay time with the different parameter alpha, and the measured result were well matched with the theoretical lines like this. This is one example how you can implement this feedback system into actual 3D NAND. In this example, each block is divided in 8 subblocks, array 1 through 8. And therefore, if you access bottom line, for example, number 2, then these switches simultaneously turn on. Then voltage is bottom voltage enters from the left hand side. You just add additional switch at the furthest node of one of 8 subblocks. In this example, number 8. And this node is transferred to this comparator, and you get the feedback loop like this. If these additional switches can be placed and the array, the actual die size impact is very small, like this. The first and second priors are for a flat panel display and 3D NAND case. So both requires additional test time or additional cost for die size increase, but they can do the calibrate the pulse width or pulse height. However, if your word line has large temperature variation, that variation cannot be calibrated with either method, because the first case you just calibrate at the very beginning of operation. So during the operation, if the temperature varies, there is no way to calibrate again. In the second method, this is just done during probe test. Once you ship that die, there's no way to calibrate further. On the other hand, using this proposed feedback circuit system, you don't have to do any calibration process or additional test. You can always get optimum pre-versus pulse even under the temperature variation, because this feedback system is effective in every single operation. In summary, a pre-versus pulse generator which doesn't need calibration before use or in product test was proposed with very small amount of overhead. That's it. Thanks.